Hello everyone, my name is Naixu Guo, now a master student at Osaka University. Today, I'm going to introduce my joint work with Kosuke Mitalai and Keisuke Fuji. The title of our work is Nonlinear Transformation of Complex Amplitudes via Quantum Singular Value Transformation. This video is for the 20th AQIS. The outline of this talk is shown in this page. First, I'm going to give a background introduction about the fundamental linearity of quantum mechanics and what is a neural network. Then, I will introduce the main ideas of our work. After introducing a previous technique called quantum singular value transformation, I will describe the construction of our methods. Finally, I will show how our methods can be used for the quantum neural network task. For people who are familiar with quantum mechanics, it is common knowledge that the quantum operation is a linear map defined on Hilbert spaces. What may happen if someone allows some nonlinear operations? It has been shown that with these operations, quantum computers can solve NP-complete problems in polynomial time. Since NP-complete problems are really hard, we do not believe that nature can have such big power, and this implies the fundamental linearity of quantum mechanics from a computational aspect. The only achievable linearity is measurement projections, so it is highly non-trivial to perform the nonlinearity with these two actions. As a fundamental interest, we wonder how much can we implement the nonlinearity with quantum computers. For example, can we perform a nonlinear function on the amplitudes of quantum states? At last, we found the answer is yes if we can find functions to satisfy some conditions. To formalize our consideration, first we want to introduce the problem, which we call the nonlinear transformation of complex amplitudes. The problem is defined like this. Assume we are given an oracle, which can prepare a quantum state, and nonlinear functions P and Q. The aim is to construct a quantum circuit, which finally outputs a state that is an epsilon approximation of the state, whose real and imaginary part of previous amplitudes are performed with functions P and Q separately. Here, I want to explain the reason why we divide amplitudes into real and imaginary parts. To perform the function on the amplitudes, first we have to extract the amplitudes information to something easier to deal with. The street strategy is to encode these into the eigenvalues of quantum gates. As quantum gates are all unitaries, we can now encode the complex numbers, and we need to achieve this part by part. Also, here we also consider function P and Q as complex functions, and this function can be more general if we define it in this way. We find that this problem is not only fundamentally interested, it also has practical applications, such as to perform the neural network task on a quantum computer. The neural network is the most widely used method in machine learning field. This method uses a mathematical model for information processing based on a connection of probes to computation, and the image is shown here. Here, each node denotes two arithmetics, linear transformation and nonlinear transformation. It has been shown that every continuous function that maps intervals of real numbers to some output interval of real numbers can be approximated arbitrarily closely by a multi-layer perception with just one hidden layer. This theorem promises the effectiveness of neural networks. Here, I want to explain the computing process of neural networks in details. For example, consider L's layer of neural network. Its computing process can be written in this matrix form. The matrix W in the equation is a weight matrix, which aim is to redistribute the sample data. P denotes the nonlinear function, and mostly people use tangent H and rule function to implement the nonlinearity. Neural network can be used for the task-like regression or classification, which has many applications to modern society. From the common computing aspect, it is also very interesting to consider how to perform this method in quantum. To implement the quantum neural network, there are some previous works, and here we list them together. Because of the linearity of quantum mechanics, all of work consider performing the linear transformation with quantum, where they can provide a speed up compared with classical case. However, each work will consider different methods to perform the nonlinearity. The first paper uses a circuit, which they call repeat success. It is composed of many control rotations. It is very easy to implement, however, they can find data as binary. The second work performs the nonlinear transformation with classical computations. After linear transformation, they read out the data from quantum and implement linearity. After that, they encode the data back to the quantum. The problem is that reading and read out may cost much in practice. The third work uses phase estimation and quantum arithmetics to perform linearity. It is useful for any function, yet they need many ancillary qubits. Our work is actually based on the hint from the third one and the previous work they called quantum singular value transformation or qubitization. We can use less ancillary qubits, and our complexity has better dependence on error. The problem is that the method is not suitable for all functions. After introducing the background of our work, now I'm going to describe my ideas. It is divided into two parts. First, I will explain the idea of previous work to SVT, and then show how we can use this subroutine to achieve nonlinear transformation of complex amplitudes at task. Here, I want to introduce the definition of block encoding. A unitary U is a block encoding of matrix A if A is kind of encoded into this unitary, like the matrix formed on the right side. Let us consider a singular value decomposition of this matrix A. Actually, they have shown in the paper that for some d-degree nonlinear functions P, which satisfies the conditions of quantum singular processing, one can construct a circuit that can perform function P on the singular values of matrix A. The circuit is described in the following. Here, one can see that circuit uses U and U dagger respectively. The reason to perform the circuit in this way is to keep operations acting in the desired subspaces. Between these two gates, there are also controlled gates and phase rotation adding on the ancillary qubit. Here, phases are chosen to perform the desired function P. Our idea is to perform nonlinear transformation on the amplitudes by QSVT. So our aim is to construct a unitary, that is a block encoding of a matrix, part of whose singular values are the real or imaginary part of the current amplitudes. For simplicity, we will consider the real part in the following. In the next phase, I will introduce the exact construction. However, it is very complex and I want to summarize the conclusion first. After contrasting the desired unitary, we use it to perform QSVT and amplitude amplification. Here, amplitude amplification is to make the algorithm deterministic. To achieve the task of nonlinear transformation of complex amplitudes, the output complexity is in this value. First, it depends on the degree of the nonlinear function P. Also, it depends on the dimension of the states and amplitudes after the transformation. These two values play a key role when we consider quantum neural network task. In the worst case, the computation speed is not better than the classical case. Finally, one should notice that our dependence on error is polylog, which is exponentially better than the previous works. Now I will introduce the construction of our methods. This is a circuit of QSVT, where the delta G is constructed with the following. The construction is kind of complex, and I'm not going to explain details here. The bottom circuit is used for state shifting, where U is the state preparation oracle. This circuit can shift the prior state prepared by the oracle to some states easier to be handled. The middle figure shows the construction of a unitary G. Assume we have access to the controlled version of G and G dagger, then combined with two Hadamard gates, Taylor G can be constructed. It's easy to see that Taylor G is a block encoding of 1/2 G plus G dagger. Here is the most important part, and I want to stress the properties of 1/2 G plus G dagger. First, it is a Hermitian matrix. Second, if someone considers the singular value decomposition of this matrix, one can find that previous amplitudes are exactly the singular values of this matrix, corresponding to some states which can be prepared by the bottom circuit. As a summary, based on this complex circuit design, we can use QSVT to achieve the nonlinear transformation of complex amplitudes task. Finally, I'm going to introduce how to use this method to implement the neural network task. To implement the quantum neural network task, first, we need to consider how to perform the state preparation oracle. Based on the previous work, we know that the oracle can be efficiently achieved with a quantum data structure called QRAM. Linear transformation is considered to be implemented with parameterized unitary, and the linear transformation is achieved with our construction. One should notice that the linear, unitary, and state preparation oracle can be considered as one operation, and it will be the oracle in our construction, shown in the previous part. The mostly used nonlinear functions in the neural network, tangent h and root, can also be well approximated with our method. After computing process, we consider optimization is achieved classically. For practical uses, it is very important to consider how to implement the multi-layer neural network task. We find that in our construction, the circuit for the second layer is almost the same except for the oracle gate. Since previous construction can be considered as the oracle for the next layer, by denoting the previous construction as a neural oracle, task of multi-layer neural network is also achievable based on our method. Based on these considerations, we find that if the data is nearly uniform, one layer neural network can be computed in time square root n, where n is the data vector dimension. This is a polynomial speedup compared with classical cases. Also, the quadratic speedup can maintain for the two-layer neural network. However, for deep layer neural network, our circuit will become very complex and finally inefficient, since we rapidly use the previous layer construction as a new oracle. So the disadvantage is that it is not suitable for deep neural network task and stays as an open problem. This is a summary of our talk today. First, we define a problem called the nonlinear transformation of complex amplitudes to explore the implementable nonlinearity of quantum mechanics. Then we provide a concrete algorithm to solve the problem based on quantum singular value transformation. Because of using this technique, we can find the nonlinear functions to satisfy the conditions of quantum singular processing. It is an open problem to consider how to generalize this consideration, or how can this condition be generalized. Finally, we show how to use our method to achieve the quantum neural network task and compare it with previous works. Thank you for listening.